The instantaneous current I in the circuit is therefore given by I equal to dq upon dt equal to d by dt C E naught sin omega t equal to C E naught omega cos omega t equal to E naught upon 1 upon omega c sin omega t plus pi by 2. The maximum value of sin omega t plus pi by 2 is 1. Therefore, E naught upon 1 upon omega c is the maximum current in the circuit. Thus, I equal to I naught sin omega t plus pi by 2, where I naught equal to E naught upon 1 upon omega c is the peak value of current. A comparison of this equation with the EMF equation E equal to E naught sin omega t shows that in a perfect capacitor the current leads the EMF by a phase angle of pi by 2 or 90 degree, or the EMF lags behind the current by a phase angle of pi by 2 or 90 degree. This means that when the EMF is 0, the current is maximum and vice versa. Figure A shows this phase relationship graphically. Figure B is the corresponding phasor diagram. Capacitive reactance. The peak value of current in the capacitor circuit is I naught equal to E naught upon 1 upon omega c. Applying Ohm's law, we find that the quantity 1 upon omega c has the dimensions of resistance. It represents the effective opposition of the capacitor to the flow of alternating current. It is known as the reactance of the capacitor or capacitive reactance and is denoted by Xc. Thus, Xc equal to 1 upon omega c equal to 1 upon 2 pi Fc, where F is the frequency of the alternating current. Thus, the capacitive reactance decreases with increasing frequency of current. This is why this is easy to understand. So, at a higher frequency, the charge on the capacitor plates will vary more rapidly. dq upon dt will be higher, resulting in an increase in the instantaneous current. I equal to dq upon dt. This means lower capacitive reactance. The capacitive reactance Xc equal to 1 upon 2 pi Fc is infinite for DC, for which F equal to 0. The reciprocal of reactance, inductive or capacitive is called susceptance of the AC circuit. It is measured in mho or ohm inverse or Siemens. Now let's see circuit containing inductance and resistance in series, LR series circuit. Let an alternating EMF E equal to E naught sin omega t be applied to a circuit containing an inductance L and a non-inductive resistance R in series. As shown in figure A, the same current will flow both in L and R. Let I be the current in the circuit at any instant and VL and VR the potential difference across L and R respectively at that instant. Then VL equal to IXL and VR equal to IR, where XL is the inductive reactance. Now VR is in phase with the current I, while VL leads I by 90 degree. Thus VR and VL are mutually at right angles. Their sum is not equal to the impressed EMF E. The phasor diagram is drawn in figure B. In this diagram, the vector OA represents VR, which is in phase with I, while OB represents VL, which leads I by 90 degree. The vector OD represents the resultant of VR and VL, which is the applied EMF E. Thus, E square equal to VR square plus VL square, or E square equal to I square multiplied by R square plus XL square, or I equal to E upon under root R square plus XL square. So Z equal to under root R square plus XL square, but XL equal to omega L. Therefore Z equal to under root R square plus omega L whole square, where Z equal to under root R square plus XL square is the effective resistance of the circuit. It is called the impedance of the circuit and is represented by Z. The quantity Z measured in ohm is called impedance because it impedes the flow of alternating current in the circuit. The reciprocal of impedance is called admittance of the AC circuit. It is measured in mho or ohm inverse or Siemens. The phasor diagram shows that in LR circuit the applied EMF E leads the current I. Now let's see AC circuit containing capacitance and resistance in series, CR series circuit. In this case, the instantaneous potential difference across C and R are given by VC equal to I XC and VR equal to IR, where XC is the capacitive reactance and I is the instantaneous current. Now VR is in phase with I while VC lags behind I by 90 degree. The phasor diagram is drawn in figure B, in which the vector OA represents VR in phase with I and vector OB represents VC lagging behind I by 90 degree. The vector OD represents the resultant of VR and VC, which is the applied EMF E. Thus E square equal to VR square plus VC